Hello and welcome once again. So this class presented to you by O3 School's JAMB app, the very best JAMB app you can use while preparing for your JAMB examination. Um, you can simply download the app on either your Android phones or your Windows PC. And once you download the app, all you have to do is activate it. The activation key costs 2,500 naira. On downloading your app, you shall see the steps towards activating your app. And once you activate it, you shall be free to use the full features as shown in the app. One of the advantages of using this app is that you can try search for questions by topic so that as you read or as you follow along with this class, you shall try to be able to see questions under this topic as we treat them and then answer all the questions. All right, and now in this class, we shall be looking at AC circuits. AC circuits. Now, AC typically stands for alternating currents. Currents are of two types, either direct current or alternating current. An alternating current is simply a current which follows a periodic path such that the current increases from maximum rather, to minimum periodically. Now, the general form of alternating current is usually shown through a sinusoidal graph, such that this is I and this is time. There's an angle here, theta, obviously. And so you can see the current goes up and comes down, alternating periodically. That is the simple explanation for alternating current. Now, as it's alternating, it is starting from a certain value and moving around. We also have something now referred to as instantaneous current. The instantaneous current simply refers to the current at any particular point in time. The current at any specific point in time is the instantaneous current. Then we also have something else known as the peak current. The peak current is the maximum current that you can get in the system. As you can see, the current always rises up, reaches this peak value, and then goes back down. That value it reaches before going back down is the peak current. Now, other than peak current, there's one more thing referred to as the root mean squared current. Now, this root mean squared current is simply that value of direct current which will have the same heating effect as the alternating current in the same resistor in the same time. It's simple, kind of like imagine if you were to take a path and this should have been the direct way, but instead you end up alternating on your way. At the end of the day, this direct guy will get here and you alternating will also get there. Now, this is the root mean square current, that direct value that has the same effect as this alternating one in the same amount of time. So these are three of the important things, concepts that we must know. We represent instantaneous current simply with I, peak current with I naught, and root mean square current with I arrow S. Okay, now there's a formula to give us the instantaneous current at any point in time, because based on the fact that this is a sinusoidal graph, then we can obtain the instantaneous current as the relation is given by I equals to I naught sine theta. And if you recall from the fact that this is, kind of like a simple harmonic motion, then you should know that I equals to I naught sine omega t, where omega is the angular velocity, and that this would therefore be I naught sine 2 pi f t, where f is the frequency of this motion. So that is that. While for the root mean square current, IRMS, this is going to be given by I naught divided by root 2. Now, in some cases, they may want you to give them the answer in decimal form. So you should know that 1 over root 2 is 0.7071 I naught. So any of them. And one very important thing to please note is that all these formulas here are also applicable for the voltage. Just like we have instantaneous current, we also have instantaneous voltage, peak current, peak voltage, root mean square current, and root mean square voltage. And all you have to do is simply change your I in these formulas to V. So for example, I could be having V equals to V naught sine 2 pi ft, and VRMS equals to 0.7071 V naught. And that is the basics for your alternating current. Now, one special thing about your alternating current circuits is that other than just the resistor, inductors and capacitors, or capacitors rather, now have enough resistance to no longer be negligible. Under your direct current circuits, when you're having a capacitor in the circuit, capacitors simply acts to store charges. But in alternating current circuits, now you actually have to analyze the opposition to the flow of current brought about by that capacitor. And that is referred to as a new concept known as reactance. Reactance. And there are two types of reactance. There is capacitive reactance and there is also inductive reactance. So capacitive reactance is the opposition to the flow of current brought about by a capacitor, while inductive reactance is the opposition to the flow of current brought about by an inductor. So reactance is usually represented by letter X, but when dealing with that of a capacitor, we use XC. So capacitive reactance XC equals to 1 over 2 pi FC. Now this topic is quite simple, but it has a lot of formulas. You have to try and keep up. XC, then inductive reactance XL is given by 2 pi FL. And once this is established, then what you must then remember is that the overall reactance of this circuit will always be XL minus XC. So you have capacitive reactance, you have inductive reactance, and then if you have both in a circuit, then your overall reactance will be XL minus XC. Now, what if you now have a resistor as well as either a capacitor or an inductor? In that case, a brand new concept is introduced, and this is now known as impedance. Impedance, presented by letter Z. Impedance is the overall opposition to the flow of current provided by a resistor and a capacitor and or an inductor. That means if you have a resistor and a capacitor, you are dealing with impedance, a resistor and inductor, impedance, resistor, inductor, capacitor, also impedance. But if you have only a resistor, that is going to be a purely resistive circuit. If you have just a capacitor, that would be capacitive reactance. Just an inductor, inductive reactance, inductor and capacitor, and that would be just reactance, no impedance. Okay, so how do you get our impedance? Our impedance is given by square root of r squared plus x squared, where the x here is the overall reactance. So you can rewrite it by saying square root of r squared plus xl minus xc all squared. Now keep in mind that we may be asked to solve for voltage or current. And as you know, V equals to IR. But there will be a tiny change in this place. Because now, instead of just having only a resistor, we now have resistor, capacitor, and inductor. And both capacitor and inductor are also producing their own reactance. That means in an AC circuit, and to be precise, in an RLC circuit, that is an AC circuit containing a resistor, inductor, and capacitor, then we shall have V arrow, that's the voltage across the resistor, equals I arrow. We shall have VL, voltage across the inductor, is IXL. And we shall have that VC, which is the voltage across the capacitor, is IXC. And therefore, the overall voltage will be equals to square root of VR squared plus VL minus VC all squared. Just like the impedance is square root of R squared plus XL minus XC squared. And if you look at these two, that tells you that V, overall V, goes to IZ. And so you see, these are just tiny things you have to take note of and bring forward. And also, please, right now we are solving for instantaneous voltage and instantaneous current. If I was to be solving for root mean squared voltage, that means I'll make use of root mean squared current. That's all. So whatever I'm solving for, I'm going to use that value of current. If I'm solving for peak, I'm going to be using peak current as well. I'm solving for root mean square, I use root square current. The voltage and the current must be the same. If not, I will encounter errors in my calculation. Okay, then one more thing was to look at is resonance in an RLC circuit. Resonance. Now, quite simply, resonance occurs in an RLC circuit when the current is maximum. When the current is maximum. And how can the current be maximum? As we are aware, for the current to be maximum, looking at this, I equals to V over Z. For current to get to a maximum value, therefore, the impedance must get to its minimum value. Now, looking over here for my impedance, how am I to get this impedance to reduce? If XL minus XC equals to 0, then everything here is 0, and that gives me my minimum value. That means for resonance, SL minus XC equals 0, implying that SL equals to XC. And as you're aware, XL is 2 pi FL and XC is 1 over 2 pi FC. Now, at resonance, they usually work with a particular frequency, and that frequency is referred to as the resonant frequency. So, with a bit of mathematics, I'll be able to find out that my resonant frequency goes to 1 over 2 pi square root of LC. So once you ask for resonance frequency, this is just explain to you how we got it. This is actually what you need to calculate for your resonant frequency. And one more concept we must then look at before we are done is how to calculate the power in such a circuit. In an AC circuit, how do I calculate my power? Now, if you remember, power used to be I squared R. I cannot use I squared R here because we also have other forms of reactance. Therefore, power must be equals to IV cos phi, current times voltage cos phi, where this cos phi represents something called a power factor. And how do we obtain this power factor? We should know that cos phi equals R over Z. That is our power factor, R over Z. Okay, and once we know this for the power factor, we're able to always put this back here and obtain the power in an AC circuit. So that's our formula for power factor. And with this, we can actually move forward in the calculation. Now, please note, this topic is actually one of the simplest in physics. All you have to do is have a handy grasp of these many formulas you require. That is all. So, let's open our O3 Schools JAMB app and actually try our hands on several of these questions that have come out in JAMB. So, going to the app, our first question shall have to come from finding our question. Yes, our first question comes from the year 2001, question number 49. 2001, question 49 on your O3 Schools JAMB app. The question says, the current through a resistor in an AC circuit is given as 2 sine omega t. And we are told to determine the DC equivalent of the current. Now, like I said, your DC equivalent of any current or voltage is actually the root mean square value of that current or voltage. Like, I think I explained using this analogy. This is a direct current going straight, while this is the alternating one. Therefore, if you're looking for the root mean square value, you need to get this direct value that corresponds to this alternating current. And if you look at this representation for the AC current, or for the AC rather, compared to your formula I naught sine omega t, and then you realize that obviously these two are connected. So I naught must be equals to 2 ampere. And given that you know that root mean squared value of current equals to I naught over root 2, that means your answer will be 2 over root 2. Now, you would want to stop here in your question, but at times they may rationalize. So it doesn't matter. What do you simply do? Times root 2 over root 2. This is 2 root 2. And root 2 times root 2 is 2. 2 cancels 2, giving you answer as root 2 ampere. You see, that's our option B. And that is why you don't have to panic when you don't see your answer in the options. When you get 10, you don't see 2 over root 2, that doesn't mean you are wrong. Simply rationalize and your answer will be there. Okay, question 2. For our second question, we are going up to the year 2002 and we are looking at question number 48. At what frequency will the capacitor of 2.5 microfarad, that's 2.5 microfarad, used in a radio circuit have a reactance of 250 ohms? Therefore, at what frequency? We do not know the frequency, we know the capacitance, and we know the reactance. So all you have to ask yourself is, what formula connects these variables? And if you remember, xc equals 1 over 2 pi fc. So what do we do next? Xc is 250 equals to 1 over 2 pi times f, which we do not know, times c, which is 2.5, then micro standing for 10 to the power minus 6. Okay, now how do we analyze this? We want to get f, right? So if we cross multiply, f can go up and 250 can come down, implying that f will be equals to 1 divided by 250 times 2 pi times 2.5 times 10 to the power minus 6. Now, normally, we would have put pi as a number 3.14, but in these options, when you look at them, pi doesn't get touched. Pi remains pi. Therefore, this my pi would also have to remain pi. Now, how do we analyze something like this using our standard JAMB calculator and not a scientific calculator? How do we solve? That's the next question. We can then ask ourselves, what can we do about this? Let's start off by simply dealing with the numbers that we can actually handle. This will be 1 over 250 times 2 is 500, and 500 times 2.5 will be 1250. 1250 pi times 10 to the power minus 6. And next, look at your laws of indices. You can simply decide to either take this up, or you can simply remove this 1250 from this form and put it in purely decimal form, which means moving your point backwards. And this is minus 6. My point to go backward 6 times. If I do that, I should be getting 0.00125 pi. If you look at it, it moves back from here once, 2, 3, 4, which we are now here, 5, and then finally 6. And that means all you actually have to press with your calculator is 1 divided by 0.00125. And you see, that gives you 800 over pi hertz. And that is our answer, option B. And just for a little bit of trickery, which only works for this option, if you look at it, when I got to this point, I realized that in my solving, pi is down here, which must mean that since I'm not manipulating any longer, I just want to evaluate, must mean that pi at the end of the day must still be at the denominator of my answer. And if you look at your options, only one option has pi as a denominator. That means even without completing my solving, I should know automatically that my answer must be B, because it is the only option which has pi as a denominator. See, so in some questions, there are tricky ways to actually get your answer. And that leads us to our next question from the year 2000, question number 36 on your JAMB app. 2000 question 36. And this one tells us that a 2 Henry's inductor, that means L equals to 2 Henry's, has negligible resistance and is connected to a 50 over pi hertz AC supply. As long as my unit is hertz, I must know that I'm dealing with frequency, which is connected to this. I'm to find the reactance of the inductor. XL equals 2 pi FL. So that will be 2 pi. My frequency is 50 over pi, and L is 2. Pi cancels pi. 2 times 50, 100. 100 times 2 gives you 200 ohms. And then my answer is obviously option A. My inductive reactance is 200 pi. So you see, all you have to do is have a handle on your formulas and everything will work out. Moving on, our next question comes to us from the year 1999. 1999, question number 50. And as you can see the question, this one has a circuit diagram. We are told potential difference across the inductor, which is VL, is equal to 8 volts. But this is root mean squared, and that the voltage across the resistor, the arrow, is 6 volts, also a root mean squared value. So we have to find the effective voltage. As you are aware, the effective voltage simply means the total voltage. And generally, as we saw, total voltage is square root of V arrow squared plus VL minus VC squared. But in this case, I don't have a capacitor, which means that VC must be 0. If VC is 0, then this reduces to V arrow squared plus VL squared, because VL minus 0 remains VL. And so you see from here, I still have to put in my numbers. V arrow is 6 squared and VL makes that 8 squared. 6 squared is 36. 8 squared is 64. And 36 plus 64 gives you 100. And the square root of 100 is 10 volts. Root mean squared. And so you see, our answer is option B. One more time, just keep your formulas in mind and everything works out. All right. Question number 5, or in this case, gotten from the year 1999, question number 3. 1999, question 3. We are told in this case, in a series RLC circuit at resonance, the voltage across the resistor and the inductor are 30 and 40 volts respectively. Voltage across the resistor and voltage across the inductor are 30 volts and 40 volts respectively. So remember, when analyzing, you have to use respectively implies that the first one comes first, second one comes next. Then we have been asked, what is the voltage across the capacitor? Across capacitor. You must remember, at resonance, XL is equals to XC. Now you may look at this and go, yes, but nothing about this mentions voltage. Just remember, if I want to get voltage, what do? I simply multiply my currents. And in this case, both my currents are the same value because it's a series circuit. Therefore, current, when I multiply, I times XL must be VL and I times XC must be VC, implying that my VL is going to be equal to VC. And the VL is 40, therefore VC must also be 40 volts. As you see, one more time, keep your formulas in mind and follow the steps. Okay, let's take one more. This is from 1998 and this is question number 46. 1998, question number 46. And in this one, we have a circuit diagram. It contains a resistor, an inductor, and a capacitor. And we are being told to find the resonance frequency. If you remember, for a resonance frequency, all you have to note is FO equals to 1 over 2 pi square root of LC. So you don't have to do too much solving. Your inductance is given to you in the question as 8 millihenries, which is 8 times 10 to the power minus 3, while your capacitance is given to you as 5 microfarad, which is 5 times 10 to the power minus 6. Therefore, F naught equals 1 over 2 pi times the square root of L is 8 times 10 to the power minus 3, and C is 5 times 10 raised to the power minus 6. So let's see. Again, looking at your options before you solve, you realize pi comes out in their option, implying that I don't have to put pi for any value. So I can proceed and say, okay, 1 over 2 pi square root of. Next, I know the common question becomes, how can I solve something like this without the scientific calculator? It's very easy actually. You multiply the numbers first. 8 times 5 gives you 40 times 10 raised to the power minus 3. Because they are multiplying, I simply add my powers. So that gives me 2 pi square root of 40 times 10 raised to the power. Plus times minus is minus. Minus 3 minus 6 is minus 9. Now, typically, you could have been like, okay, how then do we find the square root? Finding the square root when it's an index form there, when you have this, is quite easy actually. All you have to do is, first of all, make sure that this is an even number and not an odd number. How can I do that? I could simply move my point from this place backwards once, implying I'm going to add 1 here. That gives me 1 over 2 pi square root of 4 times 10 raised to the power Minus 9 plus 1 is minus 8. And now, how then do I get the square root? This is actually the easiest part. 1 over 2 pi times, what's the square root of 4? Square root of 4 is obviously 2. And whenever you have power like this coming out of the square root, simply divide the power by 2. That becomes 10 to the power. Minus 8 divided by 2 is minus 4. As you see, just like that, that comes out. And then you have, let's finish it up here. And then you get 1 over 2 times 2 is 4 pi times 10 raised to power minus 4. Now, I can divide 1 by 4. 1 divided by 4 gives me 0.25. Then this raised to power minus 4 can go up, giving me times 10 raised to power plus 4. But pi remains down. And next, putting this in full figures will be 2,500. As you are aware, the point is move forward 4 times. 1, 2, which brings it here 3, 4. So over pi hertz. So my answer is 2,500 over pi hertz. And so you see, AC circuits, quite simple. Okay, let's just take a few more and we shall call it quits on this topic. Let's move on to the year 1997 and take a look at question 37. 1997 question 37. That will mark our 7th question. In this case, we are told the voltage of the domestic electric supply is represented by the equation V equals to 311 sine 314.2 T. 311 sine 314.2 T. And we're told that pi equals to 3.142. We are to find the frequency of the supply. This is actually very, very easy. Here's what you do. Simply tell yourself V equals to 311 sine 314.2 T. But you know that the equation for voltage should be V naught sine 2 pi f t. Now, as you see, that means V naught must be 311. And because there's T here and there's T here, this and this must be the same, implying that 2 pi f equals to 314.2. Therefore, f must be 314.2 all over 2 pi. But as we're told, pi is 3.142. So 314.2 divided by 2 times 3.142. Now, if you simply place this into your calculator, 314.2 divided by 2 and divided by 3.142, that will give you 5, or rather 50 hertz. And so you see, it is truly that simple. Just keep on thinking about your formulas and doing the proper analysis. In the same year, 1997, looking at the question 36, we are told that the power dissipated in an AC circuit with an RMS current, this is question 8, the RMS current, that is RMS, was 5 ampere. RMS voltage was 10 volts, and the phase angle, which is phi, was 60 degrees. We have to find the power. Quite simply, if you recall, power equals to IV cos phi. My I is 5, my V is 10 times cos 60. And cos 60, as you must know, is a special angle. These are some of the angles that you have to memorize, even if you do maths or not, because you may see them in your physics. So 5 times 10 is 50, and you should know that cause 60 is 1 over 2. So 50 over 2, and you get 25 watts. So you see, one more time, AC circuits. Very simple. Okay, and now finally, our last question on this topic. Please go to the year 1995 on your O3 Schools JAMB app. 1995, question number 48. In the year 1995, the question 48. This one states that an alternating source is connected in series to a capacitor of capacity 10 raised to power 3 root 3. So this is question 9. And capacity of capacitive reactance of 10 raised to power 3 root 3 ohms, and the resistor of resistance 1000 ohms. And so we have been asked to find the impedance of these circuits. And if you may recall, impedance Z equals to square root of R squared plus XL minus XC squared. And my resistance is 1000 squared. Then XL is 0. 0 minus XC is minus XC. But as you are aware, if you square a negative number, this is minus XC squared. If you were to do this, minus times minus gives you plus. You simply have just XC squared. So I'll simply have 1000 root 3 all squared. So that will give me 1000 squared as 1000 is 3 zeros. So the square of 1000 must come with 6 zeros. Then 1000 root 3 squared will be, again, root 3. Let's just do that here. For those of us that are not quite good at the mathematics of things like this, because your calculator will not have that. So 1000 times 1000 is 1 million, just as above. And root 3 times root 3 is simply 3. So that will become 3 times this, which gives you 3 million. So that's 6 zeros. And because the number of zeros are the same, you can simply just add them and say 1 plus 3, 4. And that's 6 zeros as well. And to get the square root of this, you could simply use your calculator, or you could remember that this is 4 times 10 raised to power 6. And that the square root of 4 will be 2. And then to get the square root of this power, simply divided by 2. That gives you 10 raised to power 3, which is 2000 ohms. And so you see, alternating circuit, very simple. I want to thank you for watching this video. Please like, subscribe, and you can follow the link in the description to go download your O3 Schools JAMB app. My name is Athanasius. Thank you again for listening.